This is the third in a series of little podcasts on quantum mechanics, electron configurations, and atomic theory, but not in that order. Okay. Electron configurations are a shorthand method of describing an electrons and atoms, and it's the offshoot of the quantum mechanical model of Schrödinger. And what we are able to do is designate the energy level, and therefore the orbital, for each electron in an atom, and this is a cornerstone of chemistry. The notation is very straightforward. Since hydrogen has one electron, we say that it is 1s1. For helium, with its 2 electrons, we go 1s2, and for lithium, 1s2, 2s1. Well, where does all that come from? Okay, we have what's called the longhand notation, and again, we go through and come up with and some other definitions we need to work with. We have valence electrons and we have core electrons. Core electrons are in what are called complete energy levels. Valence are the last electrons that are in. And we come up with a shorthand notation where we can actually show the core electrons as being like neon. The 1s2, 2s2, 2p6 is indeed the electron configuration of neon. And you're going, what? Well, this is the case where we're trying to show you some results before we go through with the rules. Okay. The rules are very simple. Okay. Electrons are added one at a time to the lowest energy orbitals available until all the electrons of the atom have been accounted for. And here is, in actual fact, a little built-up diagram following Aufbau, the German for building up, to show you that the energy level the first energy level fills first, then the second, then the third, but not completely. You will notice a minor little wrinkle there. And so we need to, in fact, add electrons one at a time as we are going through and looking at various compounds. It seems rather crazy, and it is. But you'll find that after a first look and saying, oh my goodness, I think, in fact, you'll be able to do this pretty well. You do have to obey the Pauli exclusion principle, and that is that no orbital can hold more than 2, and you'll notice here's the 2 different spins, one up and one down. And indeed, the other thing we're going to come up with a little bit later on is something called Hund's rule. But these are 3 rules with names that you need to know. Aufbau, lowest first. Pauli exclusion, 2 electrons max per orbital. Hund, stay unpaired as long as possible. So we'll get there. There is a filling order. Well, how do you know? You know that you have to fill the lowest energy orbital before starting another. If you were to pour water into a glass, it will fill from the bottom up. That's just how it goes. If you're looking at a whole bunch of CDs sitting on a shelf and they're all the same CD, you'll probably buy the one with the lowest price on it, not the one with the highest, okay? Now, how do you know the energies of the orbitals? That, again, is where this periodic table comes in. There are patterns on the table, okay? First of all, the rows correspond to the energy levels. Row 1, energy level 1. Row 2, energy level 2. 3, 4, and so on. Turns out that the s orbitals are the lowest energy orbitals or sublevels within an energy level. So the s's fill first. Well, look, they're on the left of the table. Then the p's fill. See, they're next in order. Then we get to the transition metal d's, and then we get to the f's. Okay? And so what we end up with is 1s orbitals all the way down. Then we have the 2p's through 7p's. There are no 1p's. And then the 3, 4, 5, and 6d's. There are no 1 or 2d's. And then the f's are at the bottom. And you notice the n-1, n-2. And if you go in order, you'll notice that the 4s fill before the 3d. And I have a little pattern here that shows you. You just let this thing run one at a time. And as it goes through, you will notice the electron configuration builds. And they go in order. Okay. There are some slight wrinkles that will occur in the middle of the D's, and we're not going to concern ourselves with that. And we go in order. You will notice that in the dark pink on the far right, they all end 2p6, 3p6, 4p6, 5p6. And as we keep going, eventually we'll get there. Now, here's where a little wrinkle occurs. We get to the 6s2. Now there's that star, and this is where they drop that down on the periodic table, and now we're going to fill the f's. The so-called f orbitals fill. Once the f orbitals are filled, we go back, and if you look at the actual atomic numbers, you'll find you get to lanthanum number 57, cerium is 58. We go through the lutetium is 71, and then we come back up to hafnium at the number of 72. And we keep going, and the whole thing walks through, and we end. And if we kept going, we'd end up at 7p6. So they fill in order. And there are patterns, okay? So look at the patterns. The period number is the energy level. If you're in the A group, or B group as it's called, if you're in the first, second, 13th through 18th row, we used to be called the A group. That's 1, 2, and then minus 10, 3, 4, 5, 6, 7, 8 electrons. And then the numbers of columns there, you'll find in the S block, there are 2 columns, so there's 2 electrons in that sublevel. Over on the far side, from rows 13 through 18, there are 6 there. There's 6 electrons. There's 10 valence electrons possible in the transition metals. That's the metal block in the middle from scandium to zinc. And then way down at the bottom, you'll find there are 14. Those correspond to the Fs. Okay, let's have a look at hydrogen. Hydrogen, we say, is 1s1, meaning first period in the S block, and it's in the first column. That also means that its electron is in the 1s orbital, the lowest one possible. Let's look at germanium. Germanium's a little different. It's element number 32, so it has 32 electrons. Argon is going to be totally filled. It's going to be totally filled up to argon, and we can use the square parentheses to represent the 1s2, 2s2, 2p6, 3s2, 3p6 of argon. Then, the next 2 electrons go into the 4s. Then you've got 10 corresponding to the 3d10s, and then germanium ends as 4p2. And in fact, you'll find that each little location on the periodic table corresponds to an ending electron configuration, and everything before the ending is always totally full. That's how the electron configuration thing works. Right? We have the shorthand, as we showed you, core electrons, we have the valence, and the thing you have to remember is that if we had huge paper, the periodic table would look like this. You would have the S blocks, and we just go across in order. In the yellow are the S's, then you do the P's, then you do the D's, and then you do the orange F's. And the order is based on your periodic table, and you should not have any difficulty doing the order. Okay? The sublevels in your textbook are shown as looking like this. And what happens, you see, is that as the electrons go in, as the orbitals fill, again, first level, then the second, then the third, then we do the 4s, then we do the 3d, then we do the 4p, the 5s, the 40. There are various ways of trying to remember this. I happen to prefer the periodic table. Okay, so here is another look at that shorthand core configuration, and hopefully we'll be able to explain everything that's going on. The neon electron configuration, that's what the neon shows. The third energy level, the orbital shape is S, and there's 1 electron in it. And that is what sodium looks like. It's 1s2, 2s2, 2p6, 3s1. We just simply like to say it. So let's do some. Who's the first one? Well, you look on the periodic table, you go to the 4th row, and go over 2 in that S column, and you come up with calcium. What does vanadium look like? Well, vanadium is element number 23. It's 5 over in the 4th column. What that means is that the 4s is filled, and then we're going to have 3 in the 3d. Helium, 2s2, 2p5, 2p5. That means second row, 7 over total. 2 plus 5 is 7. Or in the p block, it's the 5th one over. That's fluorine. What about silver, element number 47? Well, krypton is 36, and then we go down to 5s2, and then we go over 9 in the 4ds, and we end 49. Iodine is 1 more below that. It's 53 electrons. You have krypton. Then again, you go over, and it ends 5p5, and then fill everything ahead of time. This one's a little funny. It ends 5p6 after krypton, so if you actually got xenon, okay? And so in actual fact, you really don't need to put a configuration, although I would ask you to. I'd ask you to leave it like that. Okay. Now here we have ending 3d6. Notice everything else in front of it is full. You go to the 3d, that's the first row of the transition metals. You go over 6, okay, and you're going to find iron. Finally, seaborgium. Holy smokes, 106 electrons. Well, it's huge, but it's radon for a grand total of 86 electrons, and then add in the next 20 to get to 106. That's how this is done. So hopefully you found that useful as a little bit of a review, and indeed we'll move on from there in the next podcast.